Welcome back, Chem Team. Today's topic is potential energy diagrams. Your teacher should have given you a couple of pages in your notebook to specifically write this out and draw out our diagrams. Before we get started actually getting into the diagrams, there's a few key concepts and ideas that we need to write down and understand. So let's take a look at those. And the main key thing we're going to take away today is this idea of enthalpy, or it's going to be represented as a capital H. Enthalpy is the total energy in a reaction, and it takes into account all the different parts of energy that you can find in a chemical reaction, all the way from the potential energy that you get in the chemical bonds to the kinetic energy of all the movement of the atoms and molecules based on the temperature that they are, as well as this new concept of activation energy, which is the spark or the boost that you need to give to a reaction to get the reaction to start. So enthalpy will take all of these different types of energy and put them into, or take them into account. So it's the total energy within a reaction. We're going to typically see it as delta H, or change in enthalpy, and where you're going to look at it as the enthalpy or energy of your products minus the energy of your reactants. And what you will sometimes hear this referred to is your heat of a reaction. So your heat of a reaction is the same thing as your delta or triangle H, which basically just means the change in enthalpy for your reaction. Now we're going to focus in on this as either being an endothermic reaction or an exothermic reaction. So an endothermic reaction is when you get a positive value in your delta H, meaning that this energy you find in your products is going to be higher than the energy of your reactants, so you end up absorbing energy in the process. An exothermic reaction where you're releasing energy, you're going to have a negative delta H, where your reactants actually have more energy than your products. Alright, so the first thing is you're going to want to draw this nice and large on the rest of that first page that was given to you by your teacher. So go ahead and take a second, pause the video, and draw this diagram so that we can label it. Alright, so now that you have this drawn all over the page, the first page that the teacher gave you, we're going to take a look and see exactly what this represents. So what this is telling us here is this is telling us the reaction coordinate is another way of saying the reaction progress. So what action your reaction is actually taking or going through. And we know that whenever we look at a chemical reaction, it always starts with the reactants. So the reactants are going to be this first flat line right here. And that's going to be the energy of the reactants. So A is actually the energy of the reactants, or the enthalpy of your reactants. And your reaction is always going to end with your products. So that means D in this case, going from the bottom to this line here, is the enthalpy of your products, or the amount of energy your products have. Okay, and all our graphs are going to look the same, where they're going to end up having this hump in the middle of the graph. And what this tells us is that in order to go from or transition from our reactants to our products, we have to put energy into it to break apart those bonds and rearrange them. And that energy that we have to put into it is called your activation energy. And your activation energy goes from your reactants, because they already have this energy, up to the peak. So that bit right there is your activation energy. And you can think of it like your spark that you need to start a reaction. So you think gasoline isn't just going to automatically catch on fire. You need to add a spark to it to get it to ignite. That's kind of what the activation energy is. It's that little boost to get a reaction going. So this peak is your activated complex. It's that transition between your reactants and your products. The other key one that's going to come into play is C. And C is actually your delta H, because that is the difference or the change between your products and your reactants. And in this graph in particular, you can see that your products have more energy than your reactants. So if you were to subtract them, you would get a delta H that is positive in this case. And since it's positive, that tells us that this graph that we're looking at here represents an endothermic reaction, or a reaction that is actually going to need to absorb energy because the products have more energy than the reactants that you were starting with. Alright, let's take a look at an exothermic graph. So again, go ahead and take a second and get this graph nice and large on your paper. Okay, so now that you have this graph written in there, again, you notice it's going to have the same general shape that we saw before. The only difference is this one's going to start high and end up low. But it's still going to start with your reactants at this first line, and it's going to drop down to your products at the line at the end of your graph. So A is your enthalpy of your reactants, and D is the enthalpy of your products. And in this one, you're going to see that you have B here, which is your activation energy. And we're missing one piece, and that is the difference between products and reactants. So if we were to go between these dotted lines representing the reactants enthalpy and the products enthalpy, this is where your delta H would be. And in this case, our delta H would be negative because our products are lower in energy. So when we produce our products, they don't require as much energy. Therefore, there's extra energy left over. Energy is going to be released. So this is an exothermic potential energy diagram. Okay, so they're always going to look very similar to one another. They're either going to have the downward slope or the upward slope. The key thing you need to know is that you need to be able to find the delta H as well as the activation energy. So the delta H is going to go between, or the heat of the reaction is going to go between the products and the reactants, and the activation energy is going to always go from the reactants to the peak. Okay, it's what I've described here so far is only for the forward reaction. In class, we will talk about what it means if you have a reverse reaction. And take a look at this question, be able to answer it before you come back to class.